Hello and welcome to this Chauvin Arnoux webinar. Today we're going to give you an introduction to insulation resistance testing. Hello, my name's Kevin Smith. I'm Business Development and Marketing Manager here at Chauvin Arnoux in the UK, and I'm going to be your presenter during this webinar. For those who aren't familiar with Chauvin Arnoux, we were founded in Paris in 1893 by Raphael Chauvin and René Arnoux. Chauvin Arnoux has played a major role in the history of test and measurement. We have a long and prestigious list of inventions, such as the universal tester, the ancestor of the multimeter, and the current clamp. In the 20th century, more than 350 patents and brands were registered by Chauvin Arnoux. Just to give you an idea of some of the numbers, we have an annual sales revenue in the region of 100 million euros. We have 10 subsidiaries spread around the world, of which the UK subsidiary is one. We have around 900 employees, 7 production sites worldwide, 6 R&D departments worldwide, and we spend about 11% of our revenues on research and development. So welcome to the webinar. There's just a few things we need to go through before we get started. So the first one is testing 1, 2, 3. We just want to go through, make sure that you can actually hear everything, make sure you've got the sound adjusted properly. If you do have any problems hearing it, just check that you've got your speakers connected correctly. You might need some headphones or something like that. So just take a moment to make sure that you've got everything set up so you can hear us and everything's okay during the session. The session will last for approximately 1 hour. You can use the questions box during the session to ask any questions. And we have got staff on hand to answer those using the text function during the session. Please remember to download the presentation handouts. If you go to the handouts section on the Go-To toolbar, you will see on there that there is a PDF copy of the presentation slides that's there for you to download. So please remember to do that before you leave the session. Once the session's been completed, usually a few days later, you will be sent a certificate that basically records that you've attended the session, so you get a little CPD certificate for that. And we'll also have the video available on our website, www.cauk.tv. Again, that will be a few days, usually after the webinar. We'll put that live on our website. We'll also put that on our YouTube channel. So with that said, let's get started. So what are we going to cover in the webinar today? So we've called the webinar an introduction to insulation resistance testing. And this is very much part 1 in a 2-part series. We have got another webinar coming up next month, and that's where we take a bit more of an advanced look into some of the techniques and certainly the higher voltage types of insulation resistance testing and those techniques. So this is very much the starter. This is very much the introduction. And that session follows up and goes into a lot more detail. So we're going to start off with what is insulation resistance and how is it tested. We're going to look at some typical applications and test voltages. We're going to have a look at the insulation resistance testing requirements of BS 7671 Amendment 2. That's the new standard that's come out earlier this year in the UK. And we're going to have a look at selecting insulation resistance test equipment. And we're going to concentrate for this session, as I said, on voltages sort of 1000 volts and below. So the 5 kV, 10 kV, 15 kV testers we'll focus on in the next session. In this, we're really looking at the low voltage type applications. So what is insulation and how is it tested? Each material has a unique atomic structure with varying numbers of electrons positioned at varying distances from the nucleus. Therefore, the attractive force which binds the electrons to the parent atom varies greatly from material to material. In some materials, which we call conductors, the electrons are free to move from atom to atom with little energy required. In other materials, however, the electrons are firmly bound into the atomic structure, and therefore getting electrons to flow requires a large amount of energy. These materials are called insulators and have a very high electrical resistance. In the field of electricity, we use a combination of conductors. Remember, conductors are materials with a low electrical resistance, and insulators with a high electrical resistance to control the flow of electrons or electricity. ensuring that it only flows where we want it to go. An electric cable is a perfect example of how we use a conductor, copper, and an insulator, PVC, to make electricity literally go round corners. So this is the sort of the essence of all electrical circuits and all electrical equipment. We're using a combination of conductors and insulators to control the flow of electricity around the circuit, around cables, around an electrical system. So the concept of, resistance, particularly resistance of conductors and insulators, is really key to understanding the correct operation of electrical systems. In a previous webinar, we talked about measuring the low resistances of conductors to ensure that they're functioning correctly. We can also test insulators in the same way by measuring their very high resistance. When it comes to insulators, generally the higher the reading in ohms, the better. And typical values start in the range of millions of ohms or mega ohms. So you may hear the term mega ohm meters. That's another name for insulation resistance testers because they generally measure in mega ohms or millions of ohms. So when we're looking at readings, we're talking very, very high values. Remember when we talked about low resistances, we were talking in milliohms and micro ohms. Well, now we're talking the other end of the scale. We're talking in millions of ohms or billions of ohms. So we're talking insulators, very, very high resistance values. So if insulation is found to have a lower resistance than specified, this can mean electricity will leak through it, which could be dangerous. To measure the resistance of insulation, we need a lot of energy or voltage to be applied. There are many test voltages used depending on the circuits or equipment under test, but a value of 500 volts DC is commonly used for 230 volt AC applications. So when we're talking about testing normal low voltage electrical installations, a majority of the testing would be carried out at 500 volts DC. That's a very sort of common value. And when we think about that, if they're going to operate normally at 230 volts, we're almost using twice that voltage to verify the safety. So this is giving us a factor of safety in there, that we're actually testing the insulation at a higher voltage than it's going to operate at. And the reason we do that is really to check out the integrity of it, to give it a good chance to fail. And we know that if it can carry 500 volts DC safely, there's a good chance, obviously, that it can carry the 230 volts AC under normal conditions. So it's quite typical in insulation, this factor of using a sort of voltage that's higher than the normal operating voltage as the test voltage. Insulation resistance testing is often carried out between conductors and earth, or earth parts, and between live parts and exposed parts, such as enclosures. Insulation resistance testing is used during initial verification to ensure insulation has not been damaged during installation, but it's also an essential maintenance and fault finding test too. Insulation condition can be affected by the below, causing its resistance to decrease. So there's loads of reasons why insulation will start off in a really good condition. When it's brand new, as long as it's been installed correctly, it will have a very, very high insulation resistance. But over time, due to the effects that we're going to talk through on here, that insulation resistance can decrease. And obviously, if it decreases too low, as we said, we can get current leaking through that insulation, and that level of current could become dangerous, or it could affect the operation of the equipment itself. So causes of insulation resistance decreasing could be physical damage. So you could imagine a cable gets trapped, it gets damaged, it gets driven over, it gets, penetrated like with a nail or something like that, or a screw goes through it. Which is quite common during, installation in buildings. That's quite common, this is why we test things during initial verification. But also over time, the cable can become physically damaged, and that obviously can degrade its insulation resistance. Moisture is a very common cause of problems with insulation resistance. particularly with circuits outside and things like that. So when we're testing circuits, you know, maybe an outside light or outside socket, something like that, or maybe it could be a piece of equipment with a heating element, like an immersion heater or something like that. Again, where there's a presence of moisture can get in, and obviously water conducts better than insulation. Water isn't a great conductor, but it obviously conducts a lot better than insulation, so that reduces the overall insulation resistance and can be a sign that we've got problems with the insulation, we've got something going on. Thing with moisture, sometimes once the circuit is dried out, then potentially the insulation will recover, so the insulation resistance will go back up, and the circuit will be perfectly serviceable again. Or it could be a problem that you've actually got long-term damage, and the cable needs to be replaced or the equipment needs to be replaced. Obviously, in environments where we've got things like moisture, we can get mold or surface contamination. Temperature is also another factor. So if we've got cables that are in a particularly hot environment, maybe in a kitchen or maybe in an industrial environment where there's a furnace or something like that. And this is why it's very, very important when we're selecting cables that we choose cables that are correctly temperature rated for the environment in which they're going to be exposed. This ties in with the next one, surface contamination with things like oils and chemicals or dust. Very typical example of this is the wiring going to a cooker. In a typical domestic situation, it would be quite common for somebody to use just normal twin and earth PVC cable for that. But really, it's probably not rated for the temperatures. It's not rated for the presence of oils and other contaminants it's going to see on there. So we could very easily see the insulation resistance in that scenario of that cable going down. So this is where we've got to be very, very careful when we are installing cables, particularly in industrial areas where there might be, there could be presence of chemicals, there could be, corrosive dust, there could be, corrosive vapors and all sorts of things. We need to make sure that that insulation is actually suitably selected for that, and obviously that we monitor that over time. Other electrical stresses can cause problems with insulation. So if the cable is overloaded, again, this will cause an increase in temperature, and the increase in temperature can affect, the chemical makeup of the cable itself and cause the insulation resistance to decrease. Same with overvoltage. Again, overvoltage can cause breakdowns within the insulation, and that can lead to a decrease in insulation resistance over time. There are other environmental factors that we need to consider, and a typical one that comes across quite a lot, particularly with PVC cables, is UV, ultraviolet. So when we're outside, if we're using PVC cables outside, they will be exposed to ultraviolet, and ultraviolet can degrade that insulation over time. So it's very common to see, if you've got the grey cables outside, the twin and earth cables, and where they've been exposed to UV, you will notice that they actually get like a white sort of coating on there. It's almost bleached the surface, and in extreme conditions you'll see it goes quite hard and brittle and crusty and actually starts to break down over time. Other environmental influences are things like polystyrene. Polystyrene, when in contact with PVC, actually causes a chemical reaction. It causes the PVC to start to break down and go all sticky. So actually having PVC cables in contact with polystyrene, particularly say for like cavity wall insulation or loft insulation where they've used polystyrene, if it's in contact with the PVC, that can cause that cable to break down, and in severe cases obviously that will cause a decrease in insulation resistance. So it is very important when we're actually looking at our cables and looking at the form of insulation we've used to make sure that that insulation is actually suitable for the job in that environment. And this is why when we do insulation resistance testing, we're monitoring that to make sure that these effects haven't become too severe, where we get to the point where it's actually damaged the insulation to the point where it's going to start leaking current through, or it's going to start failing. And then obviously that could become dangerous, or the equipment could stop working. So because we're using quite high voltages, you've seen there, typically we're talking of voltages, test voltages up to 1,000 volts in this case, and typically around 500 volts. Now, the way these are applied by the insulation resistance tester, we're not talking huge amounts of current. So we're only talking very small currents, but obviously the level of voltage there, it is enough for an electric shock. So you could actually get an electric shock from these circuits. They could be dangerous. So it's very, very, very important when we carry out insulation resistance testing that we consider that we are applying dangerous levels of voltage to the installation or to the equipment under test. Now, if we're applying this to a cable, we're applying it to the whole length of the cable. Now, we might be at one end, fine. We're connecting them, we're testing at one end of the cable. There could be somebody connected, leaning on something at the other end, or especially if we're testing to earth parts and things like that, we could actually be applying that voltage to any earth part within the premises. So somebody could be touching a water pipe, somebody could be touching a tap, somebody could be in a bath, and we're carrying out this test. Obviously, we run the risk of giving people electric shocks. So you do need to be very, very, very careful when you're actually applying insulation resistance test, that you are in control of the whole test area and you've considered the full implications all the way through the installation for you actually carrying out that test. So there's a few pointers here that we're just going to go through, really just to give you some ideas of what we should do before we carry out insulation resistance testing. So the first one, A on here, it says the test must be carried out on a disconnected, non-current carrying installation to ensure that the test voltage will not be applied to other equipment connected electrically to the circuit to be tested. So what we're saying is that we should disconnect and safely isolate any piece of equipment or any part of the installation that we are going to test, and it shouldn't be current carrying. So we can't apply these tests to live circuits. The circuits must be made dead, and we should follow the full safe isolation procedures and lock-off procedures before we actually carry out insulation resistance testing. This is a dead test, for want of a better term. It's not carried out on an installation that's connected to its supply. It is not a live test, it is a dead test. So B, make sure that the circuit is discharged. It can be discharged by short-circuiting the equipment's terminals and or connecting them to earth for a specified time. So again, this is an important procedure, and when we start talking in the next webinar a little bit about the sort of high voltage testing, you will see on here that when we actually apply these test currents, equipment can become charged up to the voltage, and it can store that voltage unless it's fully discharged. It's the same when you're actually carrying out tests on circuits. Those circuits have been operating at mains voltage, so if there is any capacitance in there, capacitors, things like that, they will actually store that charge. So before we carry out the test, it is essential that we actually discharge. We make sure that the circuit under test is fully discharged. Now, we are lucky with Chauvin Arnoux testers, when you actually connect up the insulation tester, if there is mains voltage present or there is a dangerous level of voltage present on the circuit, it will warn you and it won't carry out the test until that's been fully discharged. But it's good practice when you're going to test something, make sure that it's shorted out, make sure that it's been fully discharged before you're carrying out the test, because you don't want to be going in there, touching stuff that's potentially still got, energy in it. And also, after the test, and we'll talk about this after the test, but make sure that it's been fully discharged after we've carried out the test as well. We've left it in a safe condition. So C, special protection is necessary if the equipment to be tested is in a flammable or explosive environment, as sparks may occur while the insulation is discharging before and after the test, as well as during the test if the insulation is faulty. So again, we talked about just knowing your environment, being in control of your environment. We are using voltages that could cause a spark. So if there's a fault or there's piece of equipment that are quite close together, we could get a spark. So if we're in environments with potentially explosive atmospheres and things like that, we've got to be very, very careful. So always consider that. And if you are carrying out testing in any areas like petrol station forecourts, for example, you need to be well aware of the precautions. And obviously, if in doubt, just don't carry out that test because it could be potentially disastrous. D, Because of the presence of DC voltages which may be high, it's advisable to restrict access for other personnel and to wear individual protective equipment, i.e. protective gloves, for electrical applications. So yeah, just think about your PPE in this case. You'll often see in many pictures of people carrying out these types of tests that they are wearing insulating rubber gloves. Many electricians will look at that, they'll laugh at that, and think it's overkill to be wearing these. But it is becoming more common practice, particularly when testing, that electricians are carrying out, tests with rubber gloves, with face shields and all these sort of things in place. And realistically, you can't take too many precautions when it comes down to this sort of thing. So it's definitely worth spending that extra bit of time, that extra bit of money to get the proper PPE and actually, put these things in place. It also mentions there about restricting access to other personnel. We talked about, the fact that your insulation resistance test can actually travel, down the cables through pipe work, through structural steel work and all these sort of things. So it is important to think about the impact of the test you're carrying out, and is there anybody else within the installation who could be injured, and how can we actually, keep them safe? How can we keep them out of the testing area while we're actually carrying the tests out? So it is important. Don't just think that the test is limited to, the sort of the space that you're working in with the cables in front of you. If you're testing a cable and that cable goes, 100 meters away, you could potentially be injuring somebody that is 100 meters away as well. So we do need to think about those precautions. And the final one on here, E, only use connection cables suitable for the test to be performed, and make sure that they're in good condition. In the best case scenario, unsuitable cables will cause measurement errors, but even more importantly, they may be dangerous. So again, if you're going to be carrying out testing at 1000 volts, obviously you want cables that are rated for 1000 volts. If you're going to be carrying out insulation resistance tests, you don't want cables with bad insulation. You don't want cables with frayed ends on and things like that, where it might short or it might arc. So again, just make sure you're using, correct, safe test equipment. Always with your test equipment, again, make sure it's in good condition, make sure there's no signs of damage, make sure it's all clean and dry, particularly if you are carrying out these tests outside, and it might be wet and things like that. You've got to be very careful to make sure that you're not in that environment when you're going to actually, when it's going to become dangerous. So always ensure that you have looked at your environment, you have looked at test equipment and made sure that it's safe to proceed. So there is a lot more precautions we could have talked about before testing, but that's really a good overview of the things that you need to think about. But always remember, with insulation resistance testing, you are applying dangerous voltages. Therefore, you need to carry out, your sort of safe way of working. You need to carry out a risk assessment. You need to adhere to your company's policies before you carry these things out. So it is very, very important, and I can't emphasize that enough. So let's have a look at the precautions after testing. By the end of the test, the insulation has accumulated a considerable amount of energy, which needs to be discharged before any other operations can be attempted. One simple safety rule is to allow equipment to discharge for 5 times the charging time, the time of the last test. The equipment can be discharged by short-circuiting the poles and or connecting them to earth. All the mega ohm meters manufactured by Chauvin Arnoux are equipped with internal discharge circuits which ensure safe automatic discharging. So that's a very important point. When we actually charge up insulation, it's depending on the capacitance, it's like charging up a big capacitor. So if we've tested at 1000 volts, we've charged that up to 1000 volts, and that's going to sit there. Now, potentially, if we don't discharge it, we come along, we touch those cables, that's going to discharge through us. So we can still have a shock. Even though the test meter's been disconnected, the test meter's been put away, we've stopped pressing the test button, we could still get a shock off that. So it is important to make sure it's discharged. Now, as we said there, with all the Chauvin Arnoux products, they have an automatic discharge circuit built in. And generally on most of them, you can see the voltage as well. The test voltage is normally displayed on the screen as well. So you can see when it's discharged to a safe level. But this is something to be careful of. If you're actually, say you've locked the tester in the on position and you're moving the probe during the test sequence from conductor to conductor, obviously while the test is still live, it isn't discharging. So if you're moving from point to point to point carrying out that test, those items that you've touched potentially are still charged up until you discharge them. It'll only discharge when you finally, stop the test button and stop the test. It'll discharge whatever it's connected to. So again, think about that. If you are moving from point to point to point, you may need to manually discharge them or use a test lead or something to discharge those parts after the test. And also it's important to actually leave the tester connected for a period of time after you've stopped the test to allow that discharge to take place. So just be aware of those things. It's an important safety precaution, often gets missed. In this section, we're going to take a look at some typical insulation test applications and the test voltages used. So this is a typical application that you may come across, and sometimes you'll look on your insulation resistance tester and you'll have the values of 50 volts or 100 volts DC, and generally these are for telecommunications applications. So many faults in telecommunications wiring can be caused by low insulation resistance, and this is often due to moisture ingress. So you can imagine we've got a cable going to a property, a normal copper cable going to a property. Under the ground, we've got a bit of a break in the insulation, we've got moisture getting in, so we start to notice we've got problems with the telephone signals. And again, one of the ways to diagnose that would be to carry out an insulation resistance test. But because the low operating voltages that are used in the telephone system, and also the sensitivity of some of the equipment that's there, you wouldn't really want to go zapping away with 1,000 volts or 500 volts. So in many cases, it's just a 50 volts or 100 volts insulation resistance test that's carried out. And that's enough just to diagnose if there is a problem there. And you can actually see, that there is a drop in insulation resistance. So we actually have a product specifically designed to do this. Some of the other products have got the 50 volts and the 1,000 volts on them. But we've actually got this CA6532, and that's designed specifically for telecommunications applications. And it's got a few extra features on there as well, which are specifically designed. So I think it'll actually work out like approximate cable length and things like that as well. So that is a product designed specifically for this telecommunications testing application. But if ever you see insulation resistance testers have got a 50 or 100 volts range on there, generally it's for this reason. It's to fit in with the testing of telecommunication systems. So the next application we're going to look at is low voltage installations and equipment. So what we're talking about when we say low voltage installations and equipment is really the normal wiring systems you're going to be coming across on a daily basis in domestic situations, commercial, industrial situations, the normal low voltage wiring and equipment you're going to be coming across. So in 230 or 400 volts AC systems, a test voltage of 500 volts DC is commonly used, although this can be reduced to 250 volts DC where sensitive equipment or surge protection may be present. The use of a multifunction tester, like our CA6117, is very common to perform these tests. So most electricians, when they're carrying out this type of testing, will be using their multifunction tester that they use for doing their earth full loop impedance testing, their RCD testing. They will have an insulation resistance range on that, just like our CA6117 has. You turn to the insulation resistance range, you select the appropriate voltage, and you would carry out the test that way round. Although dedicated testers like our CA65 range are also a popular choice too. And quite often people do like having a separate insulation continuity tester because it just means it's a bit quicker, it's a bit easier to use. Somebody can carry out testing using that while somebody else is using a multifunction tester to do other things. So they are quite a popular, particularly if you're doing specific types of maybe maintenance work and that, where really you're not doing full electrical installation certificates and full tests all the while. but you might be doing bits of fault finding where, you know, carrying out installation resistance testing is useful. So you might be using a multifunction tester, you might be using a dedicated installation continuity tester to carry out these tests, but this is a very common piece of equipment, and this is the sort of testing that an electrician would be doing day in, day out on this type of installation. Now, the other application, and again, this sort of crosses over more with what we're going to talk about in the next webinar, is preventative maintenance. So periodic monitoring of insulation resistance for items such as motors, transformers and the like can provide advance warning of breakdowns. While this can be done using test voltages like 500 volts or 1000 volts DC, this is typically an application for higher voltage insulation testers and will be covered in our next webinar. So generally, when we're talking about things like motors, the insulation is in such, you know, has such a high insulation resistance value that potentially 1000 volts isn't really enough to actually fully see the effects and to actually get accurate measurements. So we would need to go to higher voltage testers, and we'll have a look at that, as I said, in the next webinar series. So that was just really a few applications there that we can use. Telecommunications, we can do the normal electrical installations, and preventative maintenance. These are the sort of things that we would be carrying out when we're doing tests with what I would call a normal, a standard insulation resistance tester, something with 1000 volts or less test voltage. Now we're going to take a look in a bit more detail at the requirements of BS 7671 Amendment 2. This is the new wiring regulations that were released in the UK earlier this year. So the requirements of BS 7671 2018, which is the 18th edition of the wiring regs in the UK. Earlier this year we got Amendment 2. So Amendment 2 has made some little changes that we want to discuss here during this webinar. So in the UK, testing of low voltage installations is specified within BS 7671. And guidance is provided within IET Guidance Note 3, and you can see a picture there of IET Guidance Note 3 there, and that's really where we get all of our information from when we're looking at how to test this type of electrical installation. Now, when Amendment 2 of BS 7671 2018 came out and was published earlier this year, there was a key change included relating to the testing of insulation resistance. So Regulation 643.3.3 relates to the testing of sensitive equipment at 250 volts DC. So that's the specific bit that's changed. This is the nuance that's come into the testing. So let's just have a look at that in a bit more detail. So in the past, where equipment connected to a circuit could be damaged by the test. So remember, when we were actually carrying out insulation resistance testing, some sensitive equipment could be damaged by the voltage that we're applying. So if we've got some sensitive electronic equipment, actually applying 500 volts to it from an insulation resistance tester could potentially damage that equipment. It's quite rare. Most equipment now has got surge protection, or it's designed to actually cope with these levels of tests, but it can happen, and you know, I am aware of cases where it has happened in the past. So it's something we always have to be careful of when we're carrying out insulation resistance tests and the chance we're going to damage equipment. So in the past, where equipment could be damaged by the test, or the other option is it could influence the test results. So something like a neon light, for example, if we've got a neon light on, say, a cooker switch, that neon light can't be damaged by the test, but it may influence the results. It may cause the insulation resistance to appear lower than it actually is. So there's two things there. One, equipment could be damaged by the test, or two, we could have equipment there that's actually going to influence the results and make it appear lower than it actually is. So in those cases, previously, the insulation resistance test voltage could be reduced from 500 volts DC to 250 volts DC. So what we would do is we would drop the voltage down, and by dropping the voltage down, in many cases, that would remove the chance of damaging anything. Because remember, if we've got a 230 volts AC circuit, equipment connected to that is not really going to be damaged by 250 volts DC. There is still the possibility when we carry out tests that there could be things there that could influence the test, but in that case, we would have always in the past, we'd had to disconnect them anyway because we couldn't get a stable test. So in the past, we could just basically test the whole circuit and the equipment at 250 volts and record the results down. That was fine. But now under Amendment 2, they've gone a little step further with that. So what they've said, under Amendment 2, we must test the circuit at 500 volts DC with the equipment disconnected, and then retest it again at 250 volts DC with the equipment reconnected to it. So we disconnect the equipment and do a 500 volts test, because obviously we can do a 500 volts test when the equipment is disconnected, but then we reconnect the equipment to test it again at 250 volts. So this is actually a change. This is almost requiring us to test these things twice. Now, an important thing I've noted there on the bottom of the slide is in either case, and this was the same under the previous version of the regulations as it is now, if we were testing at 500 volts or 250 volts, we still had to achieve a minimum insulation resistance value of 1 mega ohm or 1 million ohms. So just be aware of that, because sometimes people believe because it was a 250 volt test that it only had to be 500,000 ohms, 0.5, whereas actually it always had to be 1, whether it was 500 or 250. The difference now is that we have to test at 500 with the equipment connected, and then 250 once the equipment's been reconnected. So there's a difference there. Disconnect the equipment 500 volts, connect the equipment 250. Now, I think this is more written around initial verification. So for a new installation, we would test the wiring at 500 volts before we connected up equipment. So a typical piece of equipment could be something like a smoke alarm. So we check the wiring, and then we'd connect the smoke alarm, and then we'd carry out the test then at 250 volts, so we didn't damage it or cause any problems. That's a typical application of doing this. Where I think this does call into question a little bit of how this will get interpreted in the real world is when we're doing things like electrical installation condition reports, so where we're testing installations, particularly complex installations, where there are already equipment in service, where it's almost impossible to go around and take out, every piece of equipment from a circuit. One example that always used to be talked about with this is if you've got a socket circuit with surge protected sockets. So they'd actually got surge protection built in. So to take all of those surge protected sockets out of the circuit and then do the testing and then put it back in, you can imagine it's almost impossible, because you've got bits of wire between each socket. So by the time you take it out, go around, test everything, put it all back in again, the amount of work involved in doing that, it almost makes the test moot, really, at that point. It almost makes the test impossible to carry out, or certainly very difficult to carry out. So I think there will be arguments that people will use in this when it comes down to electrical installation condition reports, and there may be limitations, or there may be, comments that people make on the test to actually say that they weren't able to carry out that test with all the equipment disconnected first. But again, there is a change in the regulations, and it has been done for the right reasons, really, to make sure that people are actually testing at the highest voltage they can, rather than, I think what was happening was people were just choosing, right, I'm just going to test everything at 250 volts because why wouldn't I? It's easier, I'll just do it 250 volts, and that was it. So I think they're now trying to put the emphasis and say, look, you need to make the effort to test at 500 volts. And the reason we're doing 500 volts is because it is above the supply voltage. We are putting this insulation under some stress. So again, I think in principle, we should carry out these 500 volts tests. However, I do foresee, particularly with electrical installation condition reports on existing installations, that it may be difficult to actually do this as per, 100% as per the letter of the regulations there. Now, just talking about the insulation resistance testing requirements to BS 7671, I think there's a few little bits maybe people haven't quite picked up on, and there's something I just want to elaborate here. It was changed a few versions ago actually in the regulations, but I don't think it's quite common knowledge with a lot of people, so we just wanted to discuss a little bit, and certainly the terminology that's used. So this is all covered under regulation 643.3.1. And it says the insulation resistance shall be measured between live conductors. So I'm measuring between live conductors. And I think certainly people who've been around a while, like I have, remember the term live being used for the line conductor. So we had the live conductor, then we started calling it the phase conductor, and then now we call it the line conductor. So when they're saying measure between live conductors, they're not just talking about, the three live conductors, L1, L2, L3. Neutral is actually classed as a live conductor. It is a conductor that is meant to be live. It's meant to be a current carrying conductor. So when they mention there that we must test between live conductors, they're saying we must check between our line and our neutral, or our lines. If we've got a three-phase system, L1, L2, L3, we must check between them, and we must check between them and neutral. So just be aware of that terminology. If we hear the word live, that means current carrying conductors. That's all of your lines and your neutral. Neutral is a current carrying conductor. So we must check between all the live conductors. And then the next bit, and this is very important as well, we must check between those live conductors and the protective conductor. So we check between them and, for want of better terms, earth, the protective conductor. But it doesn't stop there, and this is the bit that a lot of people haven't twigged, haven't understood, and it's quite clearly described in Guidance Note 3. It says we must test between the live conductors and the protective conductor connected to the earthing arrangement. Connected to the earthing arrangement. So if we are checking to a protective conductor, that protective conductor must, at the time of test, be connected, whether that's via a temporary connection or a permanent connection, to the earthing arrangement within the installation. So we can't, like we used to do, we would have checked a cable and we would have checked between the live conductors and we would have checked the live conductors to the protective conductor. But that protective conductor might have just been floating. It wasn't necessarily connected to the general mass of Earth. It wasn't necessarily connected to the earthing arrangement at the time of test. So you might say, well, what's wrong with that? Does that really matter? Well, it does matter, because actually when we're checking to the protective conductor with it connected to the earthing arrangements, that means it's also connected to the bonding, it's also connected to pipe work, it's also connected to structural steel work and things like this. So if there is a short between the live conductors and, say, a water pipe, we would pick that up by doing this test, because the protective conductor is connected to the earthing arrangement. Everything's connected to the earthing arrangement. Therefore, if we had a fault between our live conductors and something that is connected to earth, we would pick that up during this test. Whereas if we were just checking to the cable with it floating, all we are checking is that floating conductor. So we're not actually checking to the general mass of earth and the general earthing, within the installation, the equipotential bonding and all that sort of thing that's in there. So that is a fundamental change to how a lot of insulation resistance testing has been carried out in the past. And as I say, I can't remember how many versions ago, but this certainly happened quite a while ago. This test was made, certainly probably predating the 18th edition. I think this was towards the end of the 17th edition. This test was made, and a lot of people still haven't picked up on that change, that whenever we are checking between our live conductor and our protective conductor, that protective conductor must, at the time of test, be connected to the earthing arrangement. So if you're checking to the armouring of a steel wire armoured cable, that armouring must be earthed at the time. Now, you can make a temporary connection just while you're doing the test, so you could put a crock clip on and clip that to the general mass of earth while you're doing the test. That's great, you could do that, but you do need to be careful. The other reason for doing this is a safety consideration as well, because when you're carrying out that test, obviously, when you're checking to a protective conductor, that protective conductor, in the case of a steel wire armoured, for example, there could be a gland somewhere that's live, so somebody could touch that while the test's being carried out. Whereas if it's connected to the general mass of Earth, obviously there's less likely to be potential differences going on and things like that within the installation. So it just increases the safety of actually carrying out the test at the time as well. So just be aware when we're doing that test, it does make a note in the regulations there that the line and the neutral may be connected together while you're doing that test. So it would be quite common to do all of the live conductors joined together to the protective conductor. That could be quite an easy and quick way of doing it. You don't have to do L1 to the protective conductor, L2 to the protective conductor, L3 to the neutral to the... You don't have to do those 4 tests. You could just connect them all together, check them all in one go. If they pass all in one go, then that's fine. Obviously, if it fails, then you would break it down and you do them separately and try and find out which one was actually shorted to earth. But you don't have to do them individually. It does make a note in the regulations that they may be connected together when you're actually carrying out that test. So, important things to be aware of there. When we're carrying out insulation resistance testing, we check between live conductors. Neutral is a live conductor as well, be aware of that. And we check between live conductor and the protective conductor, but it must be connected to the earthing arrangement within the installation when we do that. So just be aware of those. That's not a new change, but it's something that a lot of people aren't aware of. Now at the bottom here, we've got an extract taken from BS 7671. This is table 64. And table 64 just tells us for the types of circuit that we're testing, what insulation resistance test voltage we would use, and the minimum acceptable insulation resistance values that we would come across. So we'll just go through this. So the first type of circuits on here are ELV circuits, extra low voltage circuits. So that's circuits of less than 50 volts AC, 120 volts DC. So we're talking about SELV and PELV. These are the safety circuits, separate extra low voltage, protective extra low voltage. So they are tested at 250 volts DC. So they're tested at 250 volts DC, and the minimum insulation resistance is expected to be 500,000 ohms, half a mega ohm. So because they operate at lower voltage, like I say, these are 50 volts or less AC circuits, there isn't such a requirement for the insulation to be as strong. Again, I think with all of these values, you would expect, if you're testing a new installation, you would expect the insulation resistance to be way, way, way higher than these. Even if you're testing an old installation, you would expect the values to be way, way, way higher than these. These are just the minimum sort of safe values that they record in the book. So although you see these as the specified values, you would expect, you know, these values to be multiple times higher than the values that you are seeing on here in a normal electrical installation. So that's SELV and PELV, test at 250 volts. Circuits up to and including 500 volts. So circuits with a nominal voltage up to and including 500 volts. So like our 230 volts or 400 volts normal circuits that we've got, they would fall under this. Up to and including 500 volts, with the exception of SELV and PELV. So excluding SELV and PELV, we've already dealt with those, but including FELV. So functional extra low voltage. Although the voltage is lower on that, it doesn't have the same levels of insulation, the same levels of safety built into FELV. So FELV would be tested at 500 volts in this case. So circuits up to 500 volts, so our normal 230, 400 volt circuits, and FELV are tested at 500 volts DC, and the minimum insulation resistance is 1 million ohms. So we would expect the resistance of those circuits to meet 1 million ohms. And the final one on here, circuits above 500 volts. So this is circuits with a nominal voltage above 500 volts. Now there's very little within the electrical wiring regs that would have a voltage above 500 volts. Some circuits relating to neon lighting may fall into this category. Some considerations of PV systems potentially could get into this sort of voltage range, and they are considered separately. There's different guidance a little bit on there, and we may talk about that a little bit in the next webinar about the testing of PV systems. So it's quite rare that these things will fit into, you know, there's not many circuits that fall into this bracket, but anything above 500 volts would be tested at 1000 volts DC, and it still has to have an insulation resistance value of 1 million ohms or higher. And as I said before, I would expect the insulation resistance of these circuits, particularly if they were new, to be way, way, way higher than these values. These are the absolute safety minimums. And if you did get values down this low, you probably would want to carry out further investigation. So just be aware, that's a quick run through of insulation testing to BS7671. BS7671, as I said before, is the UK electrical installation standard. So here in the UK, this would be the requirements for insulation resistance testing in a majority of electrical installations. And these are quite similar if we were testing equipment and machinery and that sort of thing as well. And to finish up today, we're going to have a look at insulation resistance testing equipment that does tests at under or at 1000 volts DC. So, as you can imagine at Chauvin Arnoux, we've got a wide variety of test equipment that you can use for carrying out these tests. So what we wanted to do was just finish up today by giving you an overview really of the products that are available so that you're aware if you're looking for equipment in this area, you know, you can see exactly what we've got on offer. So we're starting off now with a really great little product here, and this falls under the category of portable insulation / continuity testers. So it's quite common to have insulation resistance testers that also do continuity. They'll also do low resistance measurements as well. So when we look at these products, you'll see we'll have those features, but I'm really just today talking about the insulation functions of these products. But we've got here the 6528, which is a great little product. It's a very portable and compact insulation tester. Now this will carry out testing particularly suitable for the normal low voltage type insulation. So it'll do test voltages of 250 volts, 500 volts and 1000 volts DC. It's got a measurement range, really wide measurement range, which goes from 50 kilo ohms all the way up to 11 giga ohms. So we're talking way up, you know, above mega ohms, we're into giga ohms. So it's got a really wide measurement range there, and that means, you know, we've got a good range of values on this. It's got a programmable alarm threshold with backlight color indication, so you can actually set at what resistance value you want the backlight to actually change red and actually tell you that it's failed or that it's lower than you would expect. So it gives you a nice clear indication. So if you're testing quite a lot of things in one go, you don't want to be just staring at the screen all the while seeing that going up and down. You can actually hear and you can see that alarm function, and it actually tells you that the insulation has got a problem. It's also quite useful if you're testing a piece of equipment, maybe you're leaving it connected up to the instrument and you're doing some alterations, or you're wiggling some cables or something like that in a piece of equipment, and then you'll get that indication. So the alarm function is quite good on that. You've also got the hazardous voltage detection built in. So if you connect this up to an equipment and the circuit or equipment you've connected up to is still live, again, it will warn you of that and it won't let you actually carry out the test while that dangerous voltage is there. So again, that's a great safety feature built into this. So this is an entry-level product. This is really a sort of starting point for us with insulation continuity testers, but it is a great product. It's very portable, very easy to hold in the hand, and really a great addition to any sort of maintenance electrician's toolbox really, or anybody who's just starting out in doing this sort of testing where they want insulation but also a continuity function. So moving on up the scale now, we go to the next range of testers, and this is our 65 series, or 65 range. So we've got the 6522, 6524 and 6526. And these are really more advanced versions of what we looked at with the 6528 there. So there are differences between the various products in the range. So you'll see the little stars on there, and the little stars are saying depending on what product I'm talking about. So a lot of these features are on the 6526. The 6522, obviously, as you expect, will have less features on there. So if you're not quite sure, always have a look at the data sheet and you'll be able to pick out exactly which features you want. So within this range of products, we've got test voltages from 50 volts all the way up to 1000 volts, and they're selectable using the rotary knob, as you can see from the image there. Again, measurements up to, in this case, 200 giga ohms. So again, we're talking really high measurement range on these products. Now, what we also start to see is you can actually see some of the more advanced test sequences coming in here. So we've actually got the ability in here to do some tests that you'd expect to see on the higher voltage testers. So for example, we've got the PI test, the polarization index test, and the DAR test. That's included within these testers, particularly within the 6526 and I think the 6524 as well. So again, these are tests that actually would help you if you were looking at, say, testing a motor and trying to, look at the quality of the insulation or motor or transformer or something like that. So these are features you'd expect to see probably on the more advanced, more chunkier testers that we'll talk about in the next webinar, included in these products. You've also got the ability to store results. So with these, we can store up to 1,300 records within the tester. So again, we're carrying out the testing. So if you were doing quite repetitive testing, or you're doing testing where you need to, keep records of what you've done, again, with this, you can just keep storing those results. And we've also got the Bluetooth connectivity as well within the 6526. So again, we can connect that through to the PC software, and we can actually monitor the results in real time, and we can download those results via the Bluetooth connectivity. So these are really powerful little testers, and they are really useful tools for anybody who's carrying out that sort of maintenance and wants some of the more advanced features that you'd probably find on the bigger testers, but wants the portability of actually being able to carry these things around quite easily. Now, we have got very similar to the testers we just looked at, and these are also part of the 6.5 range, but this is the 6.532, 6.534 and 6.536, and these are ones that are designed for specific applications. So sometimes if you're working in a particular field, you don't want all the extra features on there. You just want it to be very good at doing what you're working on. So the 6532 is designed specifically for the telecommunications applications. So the testing at 50 volts and 100 volts DC. We've got the 6534. This is designed more for electronics and particularly ESD, electrostatic discharge. So if you're actually setting up an electronics production environment or an electronics repair environment, you will have things like static dissipative matting, and you'll have wrist straps and all those sort of things to dissipate any electrostatic discharge. They need to be tested. So with suitable electrodes, you can put those onto the matting, and you can actually test those. And again, that product is specifically designed to work in that environment and be very good at doing that job. And then going maybe a little bit more specialist as well, we've got the 6536. Now the 6536 actually does insulation resistance testing at anywhere from 1 volt up to 100 volts, and you can select that 1 volt at a time. So if you've got a specific application where you needed to do the test at 67 volts, it would do that test at exactly 67 volts, and that would be repeatable. Now, I'm told that's specific to particular aviation, space or defence applications where we need to carry out testing, and it needs to be reliable, and it needs to be exactly at a specific voltage every time. So again, that's a very specific product, but if you are in that industry and you do need that requirement, we have got a product that fits. Now, moving on to the sort of the bigger, more ruggedized insulation testers, we've got the 6541 and the 6543. And these are, as you can see, these are big chunky Pelly case type testers designed for use in extreme site conditions. So these are designed to be, to be knocked about and sort of, to be rugged and used out in the field particularly. But they are also very, very good, very, reliable insulation resistance testers. And you can see on here that they've got the ability to test from 50 volts all the way up to 1,000 volts. So the range that you would expect, and we've been talking about during this webinar. And you can see that these will actually measure all the way up to 4 tera ohms. So not mega ohms, not giga ohms, but tera ohms. So obviously a very high measurement range and a very wide measurement range on here. They've also got the ability to do the PI test and the DAR tests, and actually store the data, download the data, create graphs, all sorts of things within these products. We can actually do all sorts of insulation resistance testing. So if you are looking for a tester, to actually carry out tests from 1,000 volts down, these would really be the gold standard in that range of products. So if you want a product to carry out testing from 1,000 volts down, these really are, the sort of the great products to carry out that testing. Obviously, if we want to go into 5 kV testing, we want to go into, 10 kV, 15 kV, that's what we'll talk about in the next webinar. But these really bring the quality you'd expect from those sort of industrial products into something that's testing at lower voltages. So if you really want that reliability, you want that ruggedness for these products, then these are really great products. This is where we should be looking. So that brings the webinar really round to a close. Thank you for listening to this session. So we went through an introduction to insulation resistance testing. We started out with what is insulation and how is it tested, and we talked about conductors and insulators. We then looked at typical insulation test applications such as telecommunications and low voltage wiring and low voltage equipment. We then went on to look at the specific requirements and the changes that were brought in by BS 7671 Amendment 2, which was released earlier this year, and how that fits in. And we also took a bit more of a look at the test voltages used under BS 7671 and, the tests that we're expected to carry out. And then we finished up with a bit of an overview of the Chauvin Arnoux products that are available to carry out insulation resistance testing from 1,000 volts down. So hopefully you've enjoyed that session tonight and you've got a lot out of those topics. Now, we have got more webinars coming up. We're actually doing a webinar every month. And as I mentioned to you before, this is part one, really, of a 2-part series. So we're now going to take all the stuff we've learned in this webinar and we're going to build on that, looking at how we actually carry out insulation resistance testing, above 1,000 volts, how we actually carry out a lot of these things like the polarization index tests and stuff like that within the next webinar. So hopefully it'd be great to see you along on the next webinar. If you want to book onto the webinar or you haven't done it already, you can visit our website. So www.cauk.tv/webinars. That will take you to our webinars page. And on our webinars page, you've got access to all of the videos from all of our previous webinars. So we're starting to build up quite a library of webinars on there now. And they're also all available on our YouTube channel as well. And it'd be great to get the subscribers up on the YouTube channel. So please, if you're visiting us on YouTube, go on there, click subscribe, click like on the videos. And that'll mean you'll get access to all of our future content as we create more of these monthly webinars. So that brings the session pretty much to an end for today. So just a few things we want to cover before you go. So thank you very much for attending. It is always great to see such a good turnout for these sessions, and it really encourages us to do more of this type of content. So remember to download the presentation handouts. If you go to the go-to toolbar, you'll be able to download a PDF copy of the presentation slides. You will receive a certificate. That'll probably come through a few days by email. It'll come through a few days after the session is finished. And the webinar will also be available on demand, either on YouTube or on our website, www.cauk.tv. And if you want some more information and have a look at some of the content that we've got, please again have a look at our website, www.cauk.tv. And we've got loads of information and articles and previous videos and webinars and all those sorts of things on there. So please check that out. So thank you very much again for your time. And I look forward to seeing you on the next webinar.